Very interesting to see what is the strategy until 2025 for Gaia-X and the community. But now it's more interesting to deep dive a bit into the future, to see what is going to happen with the impact of digital technologies, data, and also how we use data to produce AI and to produce new business models and services, with our next speaker, which is Carlo Ratti, a leading professor of the MIT Senseable City Lab. Please welcome on stage Carlo Ratti. Thank you.
Thank you. Well, good morning, all. Great to be with you here today in Spain. Well, we come from the space of cities. So what I wanted to do with you in the next 15 minutes is share with you some of the changes we've seen in the data space in cities over the past 20 years at MIT, at Senseable City Lab, and also how we see things changing today. And also, I was asked to mention a few of the opportunities also for business, so I'll share something that came out of our lab, a couple of startups that just came out of our lab. But just to tell you, something like 20 years ago, we were actually the first group in the world to start looking at cell phone data to describe cities. And this was a project in 2006. We actually started in 2002 or 2003 to look at how all this kind of giant amount of data that now we collect, we are very familiar with, is what is always with us in our pockets, but at the time we're just starting, and we started looking at how it could describe a city. That, for instance, was one of the first projects we did. This was a visualization of Rome, mapping flows of people using millions of cell phone data. This was some of the initial papers. And at the time, the resolution you had was around 500 meters, and the temporal resolution, the spatial resolution, 500 meters, and the temporal resolution around 100 minutes. So what you could do with the data at the time was, for instance, to study regions. And I put this project, we did quite a few at the time, but here we looked at Belgium and actually started analyzing regions in Belgium, how they connect, how flows are structured. We discovered actually in this paper that all of the communication follows a gravity model. Gravity models are very well known in the science of cities and regions. They follow a little bit like the gravity law for planets. So, but the point is that at the time, what we could do is do this type of analysis and look at regional scale. Then you fast forward 5 years. And 5 years later, the spatial resolution has gone to 50 meters, and the temporal resolution has gone to 10 minutes. And then what you can do changes dramatically. This was a paper in Nature we had that was based on the type of data. The paper came out later, but was based on the data you could get then, where we actually can start looking at cities, the inner functioning of cities. Or this is another paper we had in Nature where we looked at mobility in New York. And here actually I'll show you a little video. And this was actually the starting point for our first startup in the space of data space, a company called Data Drive that tries to develop, call it an operating system for cities. But again, this was the result of high resolution in the data space. Here is a little video. So that was the kind of things we started doing with that resolution. Now, let's move to 5 years ago. And 5 years ago, you could say, for this space, we were getting data at 5-meter resolution and 1 minute temporal, sorry, I keep on saying 5 meter spatial resolution and 1 minute temporal resolution. And then you can start looking at the individual. For instance, a paper we did at the time is a paper was published in the end 2 years ago, but we started doing it 5 years ago. It's something that bothered me since when I was studying at Cambridge University. I was in that college called Darwin College, and I realized I was going from the college to the department following one path, and then from the department to the college following a different path. And I was concerned, I was puzzled, is this something, or is it just my brain, or is it something we all do, we don't follow? The shortest path is symmetrical, and I realized I wasn't following the shortest path. Now, I wanted to solve this with big data, but the data wasn't high resolution enough. Well, with this type of data, then we started looking, that's a paper in Nature Computational Science. Paper is from 2021, but again, based on data from 5 years ago. And we started looking at that resolution and how people move in a city. And we realized actually that our brain, for all of us, doesn't follow shortest path. We actually follow something different that you can call the pointiest path, or what people call in people studying animals, call vector-based navigation. So we try to follow a vector to our destination, which actually explains why there's no symmetry. If you go A to B and B to A, it can be slightly different. And the interesting thing is that we did this paper with colleagues at MIT who work in brain and cognitive science. The interesting thing is that probably, this evolved over time, tens of thousands of years ago, when we were in the savannah, and it was important to keep processing power. So this is actually interesting data that allows you to optimize, not as good as shortest path, but well, is good enough because then it allows you to save a lot of computational power to pay attention to other problems you might find on the way. So somehow it becomes an interesting evolutionary response to how we navigate complex spaces. And if you come to today, the data has increased even more, both from a spatial and temporal point of view. So my story here was that over the past 20 years, we saw how we went from the city scale to the building scale, now to the individual scale more and more. And that is opening up every time, as I showed before, every time you got different type of data, you can ask different questions. And I think that now there's very exciting questions we can start looking at. Problems that were impossible even to describe just 5, 10, or 20 years ago. And so I want to share with you some of the things we are working on right now. One direction is actually analyzing a lot of visual images. As you know, with deep learning, we can now analyze and process millions of images very quickly. Analyzing images actually was done in cities. 100 years ago, a lot of people were looking at the visual appearance in cities and analyze it. But of course, at the time, it was very expensive, it took a lot of time, and so on. So now with AI, with deep learning, we can do that on a massive scale. So we got a number of projects where we are looking at data from cities, in particular data from Google Street View. Sometimes we collect it ourselves. That's just, outside. Before arriving, that's just, the Google Street View card that was here a few months ago, probably before this was open. And then when you do this, you can process millions of images in different cities. You can segment them. All of this has become possible in the past few years, and then you analyze them in different ways. I think there's many interesting applications. One application we're looking at a lot is based on, we're looking at a lot of research applications, but today I was asked to focus also on application with a potential commercial value, is also looking at real estate prices. So if you look at this, we've been training neural networks on visual images and real estate prices, and we find some striking results that I will show you in a moment. But if you think about it, AI, what it does what we would do, what a skilled real estate agent would do, but it does it on a massive scale, as we were saying. So basically, think about a skilled real estate agent here in Alicante would look at the up-and-coming neighborhoods, would look at the little shop, the little bar, the cafe, the people, the type of cars, and use that in order to understand what is going on in terms of the population and the prices. Well, you can program all of that, again, with massive data. That was our first paper, understanding house price appreciation using multi-source big geodata and machine learning. This was a more recent paper from a few months ago in the proceeding of the National Academy of Sciences. And And actually, that has attracted a lot of interest. There's a number of people starting to fund similar ideas. This was an article I did in the Financial Times just when the paper came out. But basically, how this opens up potentially a new way to look at cities, and also a lot of different applications in the way we understand and manage the built environment. The second thing I wanted to mention with you, I know that in previous meetings, you talked a lot about health data. And again, with the resolution I showed you before, for the first time, we can get close to cracking what you could call the equation of health. The equation of health, when you get to that resolution, which is the individual resolution, for the first time, we actually know the environment, the urban environment, very, very well, say pollution or the local conditions. We know how we move in that environment, how we behave in that environment, so human behavior. And then, of course, we got omics, genomics, metabolomics, we got all of that. When you intersect it, new things open up that were not possible a few years ago. And we are working on that. I want to show you something we started a few years ago now, but basically we're working more and more on this because we think that this can be, with this type of data, we can finally try to better understand the relationship between the environment, our behavior, and human health. But we started a few years ago with, inspired by this map. Anybody knows what this map is? It's a very, very well-known map in planning, and it's a map by John Snow. And John Snow in London in the 19th century actually discovered how cholera was transmitted by looking at this map and by looking at the cases of cholera and the wells in London. And they finally, that allowed them to realize that actually cholera was transmitted by drinking polluted water. And so inspired by this, we said, what if we actually look today at water in cities, especially into sewage, and we use it to basically understand, call it our collective microbiome. You know, each of us has a microbiome. You know, for every living cell in our body, there's 9 or 10 viruses or bacteria living with us. And it's very difficult to monitor in real time for each of us individually right now. It will change soon. But then, you know, what about we do this at the scale of a neighborhood? So we got a collective gut, and we monitor it. So we developed a little robot to go inside the sewage system of Cambridge, and we started collecting interesting information. Here's a little video. So somehow, as I was saying, with the increased resolution, we got to the scale of health. In this case, to the scale of, a number of individuals in a city, in a neighborhood, and bacteria, actually, so the microbiome. You see, this is the type of data you get. There are standard, analysis with all they come out today from omics and NGS in particular. You need to collect, you need to also have knowledge of the city, so to make sure that when you sample something in place A, what is the catchment area you're looking at. I will not get into the detail, you find it online, but what I want to say is that This, for instance, also led to one of the companies, one of the most successful recent company came out of the lab, and that was actually called BioBot, that during COVID started sequencing sewage globally in order to look at the presence of COVID, and today is looking at many other things, anything from drugs, the presence of drugs, opioids, to, again, something that's related to the health of every neighborhood. So anyway, the little story I want to tell you was like a little, was about how data has changed in our space, the space of cities, in the past 20 years. And that's mostly because of spatial and temporal resolution. And at every scale, you got new questions. And our impression is that now is the time where, with increasing resolution, we can really tackle incredible problems that we couldn't even see a few years ago. Thank you. Oh, yes.
Thank you very much, Carlo, for the very interesting presentation.
Thank you. Okay, so we are reaching one of the big moments of the day. We know you are all expecting break.
Yes,
So,
a bit of coffee.
Let's get to it. So we wanted to tell you that it's time for the break, for coffee and breakfast, but also for 3 guided tours that the Gaia-X team have prepared for you. You can have the Gaia-X community tour, where you can find information about Gaia-X membership, sprints, clearinghouses, and hubs. The Gaia-X lighthouses discover the business cases implementing the Gaia-X framework, agriculture, mobility, and the Gaia-X digital clearinghouses at Catalogs Network, the place to obtain compliance on service level. To take the tours, you have to go to the registration desk, where they will show you next steps.
Yeah, and also remember the rule 2, which is connect with people, and you will be able to meet also the Gaia-X vice chairs, and I'm going to name each of you, and please stand up and wave to the people so they can know you. Martín Guriet, VC Legal, please, if you want to connect with her, she's there. Okay. Bert Verdonk, the VC for Ecosystem, there. Maximilian Arens, VC for Finance, is in the house. Okay, Max is not in the house. Well, maybe we will tell him. And then Mark Kuna from VC Data Space is here. So please take a picture, find Alberto, connect, gather, and learn a lot. And now let's have a break.
No.
No?
First, no.
No,
Really,
sorry.
while you do all those things, you need to remember just one thing. We expect you back here at 11:30.
No.
What time do we expect you back here?
11:45. No, like that's no, right.
11:30,
15
please.
minutes, and then you come back. Okay, right? Let's go.